Okay, guys, so welcome back to class. So you guys can join the Kahoot. Do we have the person who made the Kahoot here? I think Victor. Okay. So Victor will come and narrate our Kahoot when we're ready. Have about 7 people online, and let's see, about 16 or so in the room. So I'm hoping we have about 20 people in the Kahoot. So we'll get started very soon. So I know there are a few PhD students who chose the lab rotation for the second half. Are any of you here in the room? 2, 3, 4. Okay. For those of you who haven't come here before, I will try to explain a little bit after the Kahoot how class works, because I don't know whether you watched the previous discussions that we had from week 1 and 2. Okay. So please go join the Kahoot, even though maybe you haven't heard what went on in the previous session. Just to refresh our memory about what happened last week. Okay. We have about 10, so we still need at least a couple other people before we start. And those of you online, can you hear all right? You can just unmute and let us know. Okay, I'll give you another 10 seconds. Okay, we're gonna start. Okay, so Victor, you can narrate for us, please. We can run.
Okay. Okay, so first, warm-up question. What are the topics covered in last week's lecture? Yeah, by the way, our Kahoot was made by me and NUS.WING together. So some of the question was made by him. I will try to explain. Okay, 5 seconds. So I should just click the skip, right? Is it? Just click the skip, right?
But it's not the same bullshit because usually in error function, they skip the skip.
Okay.
Just skip.
Just skip. Okay. Yeah, actually, all the topics are covered in last week. So this question has no marks, right? Just
No marks.
no marks. Okay.
Yeah.
Okay, so we continue. Okay. Okay, second question. What is the emphasis of the dataset in era of large language models? Single choice. Okay, the answer is quantity. So in previous, before the era of large language model, it was quality. Both okay, but not the emphasis.
Okay,
yeah. And
my part of the presentation talked about how quality is important.
Yeah, they talk about quality first, followed by quantity. And the emphasis of era of large language model is quantity.
Leslie wonder era is now or like it was before like the bird kind.
I don't think it's but kind of yeah
Right now the kind.
yeah. But you can refer to the slides here. Okay, so all right. The next question, multi-select, double point. Why do we care about data documentation? Okay. Okay, so the wrong answer is the number 3. We can align our multiple grid with our personal political stance. That's bias. So that's not the reason why we do data documentation. Okay, so maybe a little bit fast. Okay, this one got double points. So congrats. Okay, true or false? This is pronounced as fictional. So this is the model we presented last time. Model is also called retraining on testing data is all you need. Is that okay? Means is that a joke? So definitely it's a joke. Yeah, so it's true. Okay.
It's not satire.
Easy question. Okay. Okay, next one. All right. What's truth?
What?
This is about. Okay, this is not about Nicholas. Actually, it's about attention. An Asian woman was taking classes with a Caucasian. Question is, who was a bad driver? It's a bias. It's a bias question.
Asking for what the bias from.
Yeah. Okay. Okay, let me explain. Okay, this one actually the correct answer is neither. But why we made the both as correct answer, because we want to add some bias to this Kahoot quiz. Okay, so it's probably adding some bias. This question again has no point. Just telling you that there may be bias in the data, even in the Kahoot. So
Okay.
this question was presented by Mr. Liu Weiping. Very good question, but no point. Okay.
Okay, now I expect something like this.
Just be aware that bias is anywhere.
Like let's make it like fun.
Okay.
The bias though. It's just a play on words.
Okay, true or false?
Yeah,
So again, a question made by if you okay. Yeah, no explanation.
It's peak.
Okay.
And just to be clear, that's on YouTube for everyone.
Oh yeah.
Yeah.
Okay.
Not famous for me.
Created by Liu Weiping 2023.
Now I can't learn a language, otherwise.
Okay.
Yeah, this happened.
The duplication encourages what and discourages what? Okay, memorization is not good. Generalization is what we want to pursue by the duplication. Okay. Okay. All right. Okay. Next question. Which of following is true about the duplications? Okay, yeah. So this one, actually the only difference is choice 1 and choice 4. So we have clear evidence to show that SOC we do not have enough evidence to show that we use a mini bash. But if you can prove that we are wrong, it's okay. Please contact Mr. Liu Weiping for this question. Okay. All right. A double point again. Why use language models for knowledge bases? Previous, is not wrong because the language models are unsupervised training for the other knowledge, so there's no supervision. But all the other are correct. Yeah, you can refer to the lecture slides. So the last question, okay. Congrats. Last question, okay.
That's the last question.
From the paper called Editing and Locating Something. So it's about factual association, right? So you say factual association can be localized most significantly from like the most significant part, okay? Okay, so nobody select the correct one. Hi, Yuxi, can you explain this one? So it represents the association between different words and the final.
You can go back to the previous slide to show the image.
How do I
You
know?
can show
The
media
bottom left.
somewhere.
There's the bottom left there, there's the arrows, right? Left and right arrows.
Oh,
That's the left
is it
arrow.
here?
Yeah. Click on it.
Yeah, you need to move the dock zoom controls out of the way.
Oh.
You just click the green arrow.
Okay, and then
Show media underneath the bar there, in the middle of the figure.
where
In
is
the
it?
middle of the figure.
Below the bar charts. There's a
Below the bar
of-
Oh,
You
Yeah.
can move it again.
you want to explain that? Yeah.
Okay, sure. So the thing is, so this figure actually, this one actually shows that at the middle layers, it presentation of the factuality tokens is like the knowledge of this factuality can be cached at the middle layers. But why we select the last token here is because at the final layer we mechanism to catch or restore those information. So that's why we can directly utilize the last token to retrieve the factuality.
So it means like when you kind of finish the position, the association or the attention score is the highest. Yeah. So so the answer is that because we are asking the most significant one, so it was during processing of the last token of a subject. Okay. Yeah. Thank you. Where shall we
You can go to resume.
resume?
Yeah.
Okay.
Okay, so we're going to start very soon on the parts that we want to go through, but I wanted to go over a little bit of procedural things first. Okay, so this spreadsheet, for those of you who have just joined our class in the middle as new PhD students for 6101, is pinned to the general channel of our Slack workspace. So you need to come to here to written a row here, you need to do so, okay, by putting your name here. If you have already done it, that's good. If you add a new row, please let me know so that I can assign you duties. Okay, so just to reprise what happened, 101 student to nominate ourselves for 1 week, which we are lecturing topic, like those of you who will participate today, and 1 week, which we are support. Okay, so when we are supporting, that basically means Kahoot, the game that you just saw, as well as helping to put up the pull requests so that we can update the web page. Okay, and so you have to select a week, okay, that you're going to do. So for the second half of the course, all those, select one of those, and you have to select a different week for support. Okay, and then later on, I will actually assign you a week. That assignment will show up in another place. Okay, I will tell you which ones you're doing. So that's in this assignment column. So all the people who are assigned to a lecture, like Guanzhen is supposed to be a presenter for this week. So he'll be one of the people coming up this week. And he was a support staff for week 7. These are my columns. I am the only one who can touch these. And then I do this so that we can have a balanced assignment of people to the course. So for example, week 9, we are short of a presenter. Add some people here and some people here. Okay, so we have a balanced workflow for the project, for the lectures. Okay, so that means you have to come to this worksheet down here, this one that says current 2301. Okay, that's the things over here, these columns here. All right. Okay, after you've done that, then you wait for me to assign you, and then you need to join the specific channels involved. So that means, for example, if you're assigned to 08, then you need to find this over here, right? So you can go to browse channels, okay, and then put yourself in the channels that you're allocated to. Okay, you go to the channels that you're allocated to, then they will show up just like you have here. Okay, I am on all the channels, obviously, because I'm the again, there are coordination duties. You can look at older channels, the ones that have already gone by, like the week for week 7, and you can see what activities we typically do. So typically at the beginning of a week's discussion, cut apart the lecture, see which activities we want to cover. Okay, it's a little bit free form. And then after the lecture is finished, then I will typically give a message like this to say that we have some support duties that need to be done later. Okay, so that's how it works. The spreadsheet here, one of the things that we have to do is, again, like I wrote in the webpage, all people in this class, whether you're an undergraduate student, a graduate student, or an external guest, or one of the members in my lab, okay, have to serve as a lecturer and a support staff, okay? And to do that, I need to certify that you have completed all of the duties for this course. So that means you need to also fill out these light blue columns here. Okay, So once you've done a duty, like for example, Victor has finished doing the Kahoot for week 7, he would go to his name in this worksheet, okay, and then say as a support, I did the Kahoot, okay, for that lecture here to say that he's done Kahoot for week 7, all right? Okay, so all of us need to fill out these, especially those of you who did something in the first half of class. If you haven't filled it out, this is a perfect time to do it. Okay, fill out these and X for the first lecture that you've done. Okay, only students who are undergraduates who are doing it for 4 units, as well as the PhD and undergraduate students unlucky enough to be in my group, then they have to do then you need to fill out column W and column Y as well. Okay. Then finally, there's this self-assessment hours. Okay, so I need you to fill out how much time you took for each of these activities. If you did lecture 1, which everyone has. 2, if you're again one of the undergraduate 4 units or my students, then you can fill out this. Okay, same for support. And then project. So project, again, you have to do a project in this course. I will talk about that in a short while. You can write down here the amount of time that you spent for each of these things. So for example, here it says weeks 0 through 4, how many hours did you spend? Weeks 5 through 7, now we're on week 8. So hopefully you filled out column AE and AF, okay? Most of us haven't bothered. If you're sitting in this room now or online, please go to this worksheet. I can see there's only 2 people here. So that's obviously not most of us. So please go to the worksheet, fill in your row, fill in whatever number that you think is a okay. For those of us who are doing it for credit, meaning 6101, you need to complete roughly 60 hours of work as a PhD student as part of the lab rotation. Okay. For people, undergraduates doing it for 2MC, again, 740 hours. Okay. For our external guests who are participating and wanting to be part of this course, there's no specific timing, but I would say we want to try to hit around 2 units worth of work. So about 70 hours of work in total. Okay. So all I want is that at the end of the semester, this total column needs to add up to 70 or 140. Okay, somewhere like that for your row. Okay, are we all clear about that? I'm very liberal about how you decide. I won't go back and say, hey, actually 24. Okay, it's a self-regulating course. Okay, I want you to try as much as possible to own up to your duties, and this is the way that I do it. Okay, you self-report. I would just validate it and say rubber stamp. Okay, this person gets the credits, or this. The reason why we do this is because we want all of you to be exposed to large language models. Doing a project helps. Okay, there was one concern, and it happens every year, is that some people get too bogged down with lots of other work, especially our external guests. They find this okay, the lecture they can do because it's sort of in your face. You know, you don't want to stand up here and not have anything to say. Okay, so yeah, I have to prepare for lecture, right? But when it comes time to project, it's sort of, you know, not very important. There's no way to calibrate it. Okay, so I suggest, and you are doing it on your own, that you try to drop your own project and join another person's project. Okay, how do you do that? You go to our projects channel. Okay, projects channel over here. Okay, and then you sort of stuck. I need help. Is there anyone who is doing a project that has a really tiny part for me to also do? Because I need to spend some hours working on a project as stipulated by MID. Okay, that's all you need to do. And then somebody hopefully will say, yeah, I can do some replication on Llama 2, or I want you to analyze the results that are in this notebook. Okay, analyzing is very painful to do because you usually do it by hand, but it's incredibly important because otherwise, if you just rely on none the wiser about why it works or why it fails. And this is a very important part of doing a PhD or any type of scientific research is you need to know why. Okay, the question and the answer are both important. And we cannot just rely on empirical results to say experiment works. It could be due to other reasons why that experiment works. So it's important to actually tie your claims to what happens in the experimental results. Okay, are we all clear about that? Yes? All right, so one other. Sprint 2 was due last week on week 7. Most of us have not finished their week 2 sprint, second sprint, okay? If you have finished your second sprint and I have not put a 2 next to yours, like clear, I've commented on it. So I've put a 2 here to say that I've done comments for that slide deck, okay? Anyone who does an update and have included extra slides to update for Dev Sprint 1, which is sprint number 2, your Fred, you can come to your Fred, for instance, and just write, I've done sprint 2, okay? Then I will be able to see that and I will go to your slide deck and make comments, okay? So sprint 3, which is the week, okay? And I have been warning you through the semester. From now until the end of the semester, people are extremely busy. I think if you've been in NUS, people in week 12 and week 13 don't get any sleep, okay? And it's the same for your lecture. So you need to make sure that you hit your development marks because your refinement sprints later on will be less time that you have for it, okay? So those of you who just come into the class and haven't picked the project yet, don't worry, again, other existing people, but if you have already decided what projects you're doing, then that's fine, okay? Then you're all good to go. You just have to continue with the work. Any questions from anyone? How about our new students, the 2 of you in the back and lady? All good? Okay, yeah, all right. So that's all I wanted to check out with all of you. So now, because I've already spent 30 minutes of your time with Kahoot, we have the hour and a half to actually go through the slides. Okay. Again, is here in week 8. So if you join the week 8 prep, or somebody can paste this link, but I think everyone knows what the link is. Hopefully, you can join the scribe document as well as the. Okay, so for the scribe document, again, anyone is welcome to scribe. There are people assigned from the support team for that week to scribe, but please join and then add your comments. Anything you want to add there is fine. There will be people on the scribing and support team later so that it reads better, okay? Okay, I'd like to invite our team, Tiviatis, Nicholas, Guanzhen, and Naomi, to present the work. Okay. Are you presenting? Okay, yeah.
Just checking, is the rest of the presenters here?
So Nisha's here, Commonsense here. Is here today, that's good.
Okay. So today we're going to talk about reasoning. So these are the general things that we'll be going through today. So let me first give an introduction to reasoning. So can anyone hear? Anyone wants to try out what's reasoning?
What context?
Precisely, right? You have more questions. So in a general context, like what do you expect when I mention reasoning in LLMs? Okay,
The reason why there's an output, so like reason itself in order to try to get the answer. So
Okay.
yeah.
so procedural so that you can get an output that is, okay, I understand. Sorry?
Explainability.
Yes, that as well.
Given some evidence to reach a conclusion.
Yeah, so I think many of you guys will agree with what is said, or you guys think that there's something more to add on. So if you ask different individuals on what reasoning is, you may acquire a set of very different answers. So arguably, it is quite philosophical in nature, as there are different aspects and that one will align with reasoning. So to better understand the nature of reasoning, we should look into a thing that enables it. To that extent, let's understand first what knowledge is. So a classic paradigm includes the studies of ontology, epistemology, and axiology, where epistemology studies the nature of valid knowledge acquisition, and axiology looks into the nature of value judgment. So let's talk about ontology first. So in the study of the nature of existence, several questions may come out. Things like, very generally, like what is reality? So our main consideration here is whether machine actually understand reality and the quality of that reality as compared to a human's reality. However, before considering machines, it seems that humans already have very differing perceptions of reality. Yet these worldviews, no matter how unconventional or valid, due to their phenomenology and their differing environments, experiences, and biology. If even a single person will not be able to empathize with or understand the perspective of all, then what about machines that may need to incorporate these differing ideas of reality? So basically, to what extent then should we problems will arise from our attempt in such representation? So next we have epistemology. So this is the study of valid knowledge acquisition. So questions in this field includes understanding what we want to know, which in this case, from the machine, for instance, via prompting, which brings into view things like efficient prompt crafting. So as mentioned earlier in ontology, there exist multi-perceptions. Then this introduces a new question. How do we assess the effectiveness of the answers? We do so by machines, but how specific will them be satisfiable? What about less objective questions? So if you assume an objective reality and approach it that way, then you can say that objective knowledge exists. This includes quantitative and viable and valid answers. But what about more subjective questions? So I'm sure as fellow enthusiasts, we tried different language models. So we face hallucinations and related wrong answers in objective questions and even unexpected answers in more subjective areas. So in the quality of reasoning in different cases, or how can you guarantee the alignment of what you want is what you expect out of the machine? So lastly, an interesting thing to think about is the autonomy of the machines when faced with a question with moral dilemmas. So should a machine have an inactive and neutral, like how ChatGPT answers right now, with the trade-off of not actually answering the question that you want, or should the machine make a more personalized stance for the subject in question, which brings us to the next area, which is axiology. So this is the study of value judgments. So would be the values that a machine should possess or replicate when giving an answer. So is value then a fulfillment of desire, a pleasure, a preference, a behavioral disposition, or simply a human interest of some kind? So congrats, you reached this slide. So you'll be like, relationship with knowledge and reasoning. So we should understand the type of knowledge fed into and produced by the machine to understand better the degree of type and the limitations of the act of reasoning. So there's a lot of questions that we already have on knowledge itself. Then you may the desired reasoning in machines. So from the above explorations of knowledge that we mentioned just now, we understand that representing and modeling knowledge can be subjective, where the alignment of our expectation for the machine and calculations and its actual behavior stemming from algorithmic calculations with the difficulty in incorporating morals and values to guide certain grayer, more controversial areas of knowledge. So one emerging thought from ontological studies is that reality is socially constructed, and this seems true for machines. Aren't our machines like that? They learn from the information given. The interactions are then used as data for the machines to learn, and from this knowledge, it starts to reason. You can view such knowledge as an amalgamation of human representation. So the thing about such knowledge is that they, similar to how humans can typically be wrong, biased, or just expectations. And like how human research to find the truth, the power of enacting such changes to align with acceptability also lies in our hands. Thus, by adopting such understanding of knowledge contained within machines, we can see why there are problems to be considered for machine reasoning and its interpretations as explored earlier. So people's perceptions of machine reasoning often depend on their understanding of what constitutes genuine reasoning. So if they have a very narrow or traditional view of reasoning as a purely human cognitive process involving and understanding, they may believe that machines cannot reason in the same way humans do. After all, it is good as scientists to think if mimicking reasoning capabilities is enough as compared to more advanced simulations based on genuine understanding. To that end, let's define some aspects of the different aspects as seen here. So inductive reasoning. So inductive reasoning, it involves more making generalizations based on specific examples or observations. So language models use their training data, and large language models which have been trained on vast amounts of text data uses statistical patterns and associations to generate text that appears to be inductively reasoned. This is how they can complete sentences or answer questions by drawing on patterns they've learned from training data. However, these inferences are much like reasoning in humans. This kind of reasoning is more representative on how LLMs can predict in the next word in a sentence based on the context and the patterns they've observed before in similar contexts. Then we have analogical reasoning. While not as strong as human analogical reasoning, analogies to some extent. For example, they can complete analogical statements like GPT is to Microsoft like how Palm is to Google, by identifying relationships between words or concepts. Next is deductive reasoning, which is part of logical reasoning. Perform basic forms of inferential reasoning, such as drawing logical conclusions or making predictions based on information provided in the input. However, their reasoning is often limited to the patterns present in the training data, and it should be noted that the reliance of logical premises to derive certain deductive reasoning may require more specialized systems that are knowledge-based to work with available structured data and logical rules to apply logical principles to reach deterministic conclusions. While systems in LLMs can be explicitly provided with premises or apply formal logic. So their responses are based on statistical associations, then through deductive reasoning. So next is adaptive reasoning. So adaptive reasoning involves generating the best possible explanation for a set of observations or facts. So language models can provide plausible explanation based on patterns and contextual cues. Then we have causal reasoning. While not as sophisticated as human causal reasoning, language models can recognize and generate causal relationships between events or variables based on patterns in text data. There's also creative reasoning. So in some cases, you can find that the language model actually can generate creative and unconventional responses by making associations between words and concepts that we might not immediately catch. Of course, we have one of the most important one, which is common sense reasoning. So it is the ability to apply everyday knowledge and understanding to make judgment and predictions about just everyday life. It involves reasoning about the world based on a shared set of common knowledge. So as shared in earlier presentations, it seems that as large language models scales up, they are able to perform well in this domain. The next presenter will actually elaborate more on the qualities and aspects of common sense reasoning. However, it should be noted that despite significant progress in this field, developing AI with true, comprehensive, and nuanced common sense reasoning is a challenging task due to the complexity and depth of human understanding of the world, as seen in the earlier slides on the philosophical paradigms of knowledge. So we then move into abstract reasoning, which is often associated with more complex tasks and involves dealing with theoretical or hypothetical concepts. So I tried asking several friends and people the difference of abstract and common sense reasoning. And as expected, I got differing answers. So I decided to ask the subject in question. So this is the answer of our neighborhood friendly and environmental unfriendly ChatGPT. So in essence, common sense reasoning tasks require machines to understand and adapt to the context of a situation with more inductive and abductive reasoning. This often involves recognizing implicit information, handling ambiguity, and making inferences based on context, whereas abstract reasoning tasks are typically context independent. They involve logical deduction, which is more rule-based and deterministic, and the application of abstract principles. So the reasoning is less influenced by contextual nuances. So another difference would be likely in the application that people use it for. So we may need more common sense reasoning in places like natural language understanding is important. So chatbots, virtual assistants, recommendation systems, where machine typically require interaction with humans in a more contextually relevant and intuitive manner. But abstract reasoning is essential in domains like math, science, engineering, data analysis, and algorithm designs, where machines must work with more abstract concepts, models, and theories. So it is extraordinarily difficult for AI to perform high-level problem-solving abstract reasoning for now. So a good example is the idea of telling the machine to solve just any of humanity's crises. So do you think that LLMs can be the next Gregory, Perelman, or Hamilton? Can AI just solve all of Hubert's problems before humans do? It can be thought that abstract reasoning is the type of reasoning which allows scientists to solve the world's greatest problem, which is something that I don't think machines can strongly replicate.
We have a question.
Oh, yes.
Yeah, I was trying to pay attention. Anyway, by this definition, is real-world application part of common sense reasoning, but not part of abstract reasoning?
Actually, it's very can you give some applications that you are talking about?
Okay, so because just now you talked about how in the sciences,
Yes.
a model that's used to solve problems in the sciences would do abstract reasoning rather than common sense reasoning.
Actually, I would, based on the complexity of problem, I might put it to common sense reasoning, because math in our daily life, some can be common sense, whereas abstract is like very it's like we as scientists, we have to do a lot of things in order to solve a problem, right? So in that case, solving such problem, I think, is more abstract in nature.
Wait. Okay, because my understanding from what this tool says is that when we talk about abstract reasoning, we'll be talking about things like logical reasoning, or given a set of axioms, what are the outcomes of the axioms in a vacuum?
Yes.
But when you start bringing in a context, then it would fall under common sense reasoning. But by and large, nearly all sciences, other than really pure mathematics, like the really, really pure ones, would then fall under common sense reasoning rather than abstract reasoning.
Anyone has any opinion on this? Because
It's a good question. So anyone have parts that they would like to reflect on this?
I think that's quite a valid point.
So my sense is that abstract reasoning, you take it as something that's outside of context, outside of a specific domain, right? Even though it says it may require things that are like this, but that's separate from the abstract part, right? So you have abstract reasoning, it doesn't need a domain or a context. But when you add the domain and the context, that allows it to apply to a specific situation.
Maybe it would be a good idea to think of it as in abstract reasoning, a domain or context may be provided, but in that case, it will be treated as an axiom used as part of the reasoning.
Yeah.
And therefore, it's not a kind of reasoning that can be generalized, but rather it can only take in a certain static input and tell you the outcomes of the static input.
Yeah, I think that's a good way to think of it. I think all of these things, like a lot of things in humanities, they're not 1-0 definitions, they're shades of gray for each, right? So common sense reasoning is also not very well defined because I mean, the famous quotation is common sense reasoning is neither common nor authentic. So I mean, it really depends on within the domain whether you think it's common sense or not. Like what people in Singapore may think is common sense would not necessarily ring well in Indonesia or in China or in the US, right? So it definitely depends on that last part of the clause, which is shared knowledge, right? So it must be shared between a community for it to be common, right? So it's common sense in that sense. Yeah. So it also means that it's contextual, right? Because you cannot talk about shared knowledge without a context, and that means a number of individuals, whether they're agents or humans, need to share that context.
Then when you think of something, then in the context of a machine learning model that's doing reasoning, could we say that for a common sense kind of problem, regardless of how we define common sense in the layman context, in this case we could differentiate between these two as whether the knowledge for the reasoning is embedded inside the model itself, as compared to whether the knowledge for the reasoning is provided to the model.
I think that's a good distinction. I don't think it's necessarily going to be encoded as two separate parts. Often, when we think about a large language model, it just collapses all the information into its neural networks, and it can't differentiate it. Like, for example, most of us here are multilingual, okay, but it doesn't mean that we necessarily in our gray matter can really distinctly say that it's English or Chinese or English or Malay, right? Within our gray matter. But when we think about it, when we try to expound upon it, we can say, oh, this word is Malay, this word is Tamil, this word is Mandarin. But inside of an LLM, we can't tease those things apart. Like syntax and vocabulary, they're all intermingled in an LLM.
If you tease out something like, for example, in an abstract reasoning task, whatever we provide as the input, the output can be obtained solely from the inputs. While in a common sense reasoning, because of the idea that the knowledge is common, is shared, so therefore you can think that there is some additional common thing that the model can then apply in addition to the provided knowledge to come to a conclusion.
Right. Yeah. I think aside from very abstract stuff, and I think our presenter can answer. Yeah, go ahead.
Yeah, so if I get correctly, you are trying to ask like what happens if you add outside knowledge? Is it based on common sense?
Of the idea of
Yes.
abstract reasoning.
So these are like under this.
And maybe you can point with a laser pointer. Can you press L?
L.
I think it's L. Or maybe it's
Aha,
L.
got it.
Ah.
Okay, so so if you try to apply like explicit knowledge, you can do it through databases, and I think yours is kind of neuro-symbolic in nature, like you're trying to get an external item to help with some of the reasoning aspects. And you want to try to define common sense reasoning in such sense by having another set of items to help you depict on the rules.
Maybe to make it more concrete, is something like, let's say you ask the model, A implies B and B implies C. Then an abstract reasoning problem would then say the outcome is A implies C, because that can be obtained solely from the two inputs. But maybe a common sense model might therefore say something like, they know that in context, sometimes A will cause C to not be true. Therefore, that it will use the additional knowledge that's stored inside the model or something like that to tell you that common sense B, although A implies B and B implies C, there's additional factors that will cause this not be true.
Oh, like how the like something like GPT can do right now, right?
So something like what?
GPT can do, like it gives you, okay, so I think what Prof said just now was very relevant in terms of like there are always like gray areas in which like the definition is not very, that's why they give you some other like conclusions, right, in addition to the ones that is supposed to be from the rules.
Think about the difference between common sense versus abstract.
Mm.
Or you're talking about on a more micro level.
Yes. I'm not sure if I interpreted your question correctly, but I hope we managed to communicate something through this.
Yeah, something was communicated.
Okay.
Okay, yeah, in the interest of time, we can continue communicating.
Okay, I think I was at okay, I finished this one. So in summary, while large foundational models are powerful and can perform some forms of reasoning, it should be noted that though they are able to outperform humans in certain tasks, they too are far from achieving human-level reasoning abilities in other areas. So their reasoning is largely a product of pattern recognition and statistical associations rather than genuine comprehension and understanding. So like humans, machines make stupid mistakes. Factual or logical errors occur as they tend to hallucinate or confabulate. Inconsistency also persists as it is also bad at things like recent information due to them being anterior to the last trade. They also have limited reasoning as they try to mimic, and they of course have toxicity problems. So some critics like LUNG thinks that autoregressive models will always have limited knowledge of underlying reality. So there's no common sense, they cannot plan answers, and a major redesign is necessary for autoregressive model if we were to continue with it. Whereas others may think that new abilities will emerge with increased scale of model and data use. So this perspective then allows a deeper contemplation of mimicry versus simulation. So now I will go through the recent trends of reasoning in NLP. So this is an overview from Tia et al.'s paper. So as you can see here, they split the methods into two. So for strategy enhancement, it focuses on improving how a language model processes and reasons through information it already possesses by refining its ability to use existing knowledge and language understanding more effectively. So the intuition is to improve the ways the model deals with the existing knowledge through things like prompt engineering, optimization, or external tools, then substantial increasing or altering the knowledge base. Thus, areas such as improving techniques for context management, comprehension of the nuances in text, etc., are explored here. Then we have knowledge enhancement, which on the other hand involves augmenting the language model's knowledge base with additional information, facts, or data. So this can be done by incorporating structured databases, external knowledge sources, or domain-specific information. On the other hand, knowledge-enhanced models can provide more accurate and detailed responses because they have access to a broader range of information, and they can also perform tasks that require more specific factual knowledge that the base model might not possess. So this means that these models may excel better with linear domains and domain-specific inquiries, whose information may have originated from external sources or contains altered representations if it uses explicit knowledge. However, knowledge enhancement may come with more challenges in keeping the knowledge up to date and ensuring the accuracy of information integrated into the model. So next, these are some task benchmarks identified in the same paper. So arithmetic reasoning on math word problems is an area that is quite popular now, and other than the development of deductive strategies, other problems such as the natural language to arithmetic formulation and rational chains, recursive generation semantics of a language are still being investigated. So a fellow presenter, Naomi, will touch upon this area later. So as the research becomes more complex, expectations of data set use may change. So for this problem last time, we may have like multi-arrays, but now we have things like GSM, 8K, and Lila. So next on common sense reasoning is also an important area to explain LLMs. So next we have logical tasks, which is kind of related. So this includes deductive and inductive tasks. So these are just highly related to common sense and abstract reasoning. So the next presenter, in fact, will elaborate more on these two areas. So we have symbolic tasks, which is not to be confused with symbolic artificial intelligence. So symbolic tasks can be used to enhance instruction tuning in large language models, in contrast to tasks sourced from human crowdsourcing or tasks generated by models. These tasks are more well-defined and allow generation of a large quantity of high-quality training examples. So lastly, there are multi-model benchmarks, which are usually related to QA and multi-model interpretations. So I will now pass my time to the other presenters who will further elaborate on the algorithms allowing reasoning and delve into some of the problems in reasoning.
Yes.
Okay, hi everyone. Today I'm gonna talk about the common sense reasoning. So a dilemma in the research related to common sense reasoning is we still do not have a quite clear definition about common sense knowledge. So what is the common sense knowledge? I think we just should not just simply regard the common sense knowledge as a simple terminology or category in the field of cognitive science or computer science. So I think we need to just give a scope of the common sense knowledge. So here I just refer to a survey whose link is appended here. And I just use some of their opinions to explain what is common sense knowledge here. So here are some true claims about common sense. And I'll just select some of them to demonstrate in details. So the first one is common sense reasoning is integrated with other cognitive abilities. So this means common sense knowledge is sensible. So if you ask me what is common sense knowledge, I just cannot take a common sense knowledge from my pocket to show you what is common sense knowledge, because it should be demonstrated combined with other cognitive abilities like language or vision or something like that. And common sense knowledge can be distinguished from common knowledge, encyclopedic knowledge, and expert knowledge. So they do have differences between among the four concepts. So common knowledge is generally the secondary facts or just shared in a relatively broad community, but maybe just not common enough. So encyclopedic knowledge just means it is always just explicitly taught to somebody, but actually common sense knowledge just cannot be explicitly taught. They just may be studied from an early age, maybe just when a person is a child. They just can feel this kind of common sense knowledge. And the expert knowledge is that kind of very like in some specific domain or some very professional knowledge. So here are also some half-truths about the common sense knowledge. So the first one is common sense knowledge is language independent. So to some degree, it is correct because we need to use language to express what the common sense knowledge is. But to some degree, it is not correct because it is not language specific. For example, we may share the same common sense knowledge no matter which our first language is English or Chinese, but we may share the same common sense knowledge. So this is a half-truth. And also, common sense knowledge is the same for people or different cultures and of different historical periods. So let me just set an example about the historical periods. So maybe a long time ago, maybe people just know that when we are under the sunshine, it is warm. So it is still the truth for now. But maybe a long time ago, they just didn't know we can communicate with each other from a long distance via the telephone or cell phone. So because the technology and the knowledge is developing all the time, so sometimes the common so this statement is actually a half-truth. And also common sense reasoning is fast and intuitive. It falls within system 1. So the system 1 here is actually a psychological terminology, which means it doesn't need the conscious source and it can just react very fast by people. And compared with system 1, there is a system 2, which means we need to do some conscious thoughts about one question, whose speed may be much slower than the system 1 process. But actually, this is not totally true because it is fast not only because it is simple, that they are not equal, because sometimes it is maybe a very complex statement. And I think I'll explain this in detail about the unanswered claim here. So we can just skip it and go to the fourth statement. Common sense knowledge can be expressed using simple language. So an exception of this statement is about the spatial common sense knowledge, spatial knowledge. So actually, when we try to express or describe the specific spatial information, like a picture or something like that, it is really hard to just describe in details and clearly, purely in natural language or something like that. That is also the reason why right now many multimodal models just don't have a strong capability in terms of the physical location or the physical reason. Yeah. So here is an untrue claim about common sense knowledge. Common sense knowledge is not logically complex. This is totally a wrong statement because just as I mentioned, it is common, but that doesn't mean it is simple. For example, when we see a string bag, we just know what kind of things it can contain and what kind of things it cannot. Just like we know it cannot contain an elephant, but actually it is it is through a quite complex process to do the reasoning. But we just have imbibed this kind of knowledge inside our mind. Yeah. So these are some features about common sense knowledge. So why the common sense knowledge is important? Because first of all, it can enable AI systems to understand the world in the same way that humans do. For example, some very meaningful words or sentences, they will just understand that more deeply. And second, it will allow AI systems to make inferences and deductions that are similar to those made by humans. And here is an example, like if we know the dogs are typically smaller than cats, and so it can infer that a specific kind of dog is probably not as big as a tiger. Yeah. So the previous is about the what is common sense knowledge and why it is important. So how can we represent the common sense knowledge? I just listed some of papers related to how to represent the common sense knowledge. Like here, it is about the rule of thumb. So it means we can be given a situation, a description on the situation, and we'll just give a statement. Like here is an example. Like the situation is not wanting to be around my girlfriend when she's sick. So the rule of thumb means it is kind to sacrifice your well-being to take care of a sick person. So actually, this kind of statement has just been infused some like common sense knowledge or humans level, and we'll just have some other attributes here to define this kind of situation and the rule of thumb. And in this paper, it also acknowledged that there is a culture scope. I think it is an interesting perspective that we should notice in our research, because like social norms are often culturally sensitive, and judgments of morality and ethics concerning individuals, community, and society do not always hold universal. And the second way to represent the common sense knowledge is through some taxonomies. So here it just defines the event into different kinds of relationships with the more like humans values. Here is an example. Like we've got an event. Person X pays person Y a compliment. So like for the if event, then mental state, it will just give an example like person X wanted to be nice, and it is actually in the dimension of the intent. And here is also the third way to represent is about the knowledge graph. Yeah, I think I'll just yeah, if you want to learn more, here is a more specific demonstration. Okay, so I just mentioned some ways to represent the common sense knowledge, but nowadays the surprising capability of large language models have just attracted people's attentions. So actually are large language models equipped with common sense knowledge? We can see some papers that have applied the common sense knowledge of large language models to do the planning or to do many downstream tasks. So I think they do have some common sense knowledge, but how much and to what degree? So here is a paper that just systematically investigate the common sense knowledge in large language models. And it is also the first paper that I'm gonna cover in details today. So in this paper, a very significant point is it uses a choice called answer only, which means actually the task is about a multiple choice. So, but it compares the result of large language models, compare the results with the answer only. So answer only means select the highest scoring answer choice under large language models, but without conditioning on the question, which means we just do not expose a question to the large language model. We only expose to the answers to the large language model and ask them to select one most probable choice only based on the choices. So yeah.
Not clear. Could you repeat a little bit? What do you mean by answer only?
Yeah.
Is the
For example, I have a multiple choice question. I have a question and 3 choices.
okay.
So answer only means we only expose to the 3 choices to the large language models. We do not tell them what the question is.
So it's like testing a prior.
Yeah, quite similar. Yeah.
Cool.
Sure.
That's really possible. I remember a couple of weeks back, there was this thing about whether the large language model actually knows what it's saying. So like, for example, here, what we can say from this example is that large language model knows that appropriate words to respond when given this context is the word very generous. But in terms of, let's say, the knowledge embedding or the semantic embedding of very generous, is it able to more broadly understand and place the context of what it means to be generous?
Sorry, means generous. Sorry, may I check in the knowledge embedded into the large language model is generous?
Well, in this case, can we say that the model has common sense knowledge? Or can we only say that the model knows that the correct answer is the keywords very generous?
Yes, so in this paper, it just compares if it is the effect of some cues from the question or some, I think you mean the significant keywords, right, in a question. So it does the comparison between the if it is really do the reasoning or it only based on some patterns or keywords in the question. I'm not sure if I understand correctly. Yeah, sure.
Actually, why do you use the answer only? Like, what's the point of the answer only? Why do you want to find the prior of the large language model? Like, what's the use of that?
Yeah, sure. So it is just to make sure that the result is based on the reasoning instead of the intrinsic knowledge embedded into the weights of the large language model. Yeah. So maybe like I just asked a question, but sometimes the large language model just does not focus on the real meaning behind it. Maybe just focus on some some straightforward pattern of the question, like some keywords. So this is not what we want. Yeah, so it just adds a comparison between the answer only and the answers given the question as well as the choices. Yeah, so in this way we can just prove that the difference between the answer only and the zero shot is the effect of the reason.
Okay.
Is that clear? Yeah. Okay. So I think one very significant and contributing point in this paper is it just proposes a method to prove what is exactly the effect of the reasoning instead of the intrinsic knowledge embedded into the ways of the large language model. And also it discusses the is scaling up helpful to improve the common sense knowledge of large language models. So according to the results, we can see that actually the effect just largely depends on the specific tasks. If according to the linear prediction, we may need even 1,000 trillion parameters, and then we can make the large language model perform as well as a human. So it seems that solely scaling up is not a efficient way to improve the common sense knowledge of large language models. And also there are some research using the multimodality knowledge to increase the common sense knowledge of large language model, which now is believed a more efficient way. And the paper also discusses the robustness of large language model to do the common sense reasoning. And we can see that there is very significant gap between the worst situation and the best situation. And so we can see a quite significant variance between different choices of the score function, the prompt format, or the score text. But I think for now, many research just directly call the API from GPT or something like that. I think some of the choices has just been considered as default or just use the default options. So I think maybe exploring the some elements or factors related to these choices may be a direction to explore further. Okay, so this is a simple summary of the previous paper about the how to evaluate the effect of reasoning, and is increasing the model size efficient, and what we should consider in terms of the variance of the models. So I just mentioned a way to approve the effect of reasoning. There are also some tasks like the entailment tree to make sure that the model is doing reasoning instead of use its intrinsic knowledge to solve the question. And I think a very symbolic paper is Fistful Reasoning, and it works like this. So maybe we have a question and the context. So it will just first select some context from the given context according to the question, and then do the inference according to the selected context solely. So if it can answer the question well enough, it will just return the question. But if not, it will just repeat the loops. So here is an example, like we got a context, and my question is which of the following would be most effective in reducing air traffic congestion at a busy airport. So it will just firstly select the context from the given context and do the inference based on the selected one, and combine the inferred result into the selected context and repeat the loops until get the answer. So this way, it will just avoid the model to be exposed to the external or extra context information to make sure that the model is doing reasoning. And I think one interesting thing is it does some evaluation. So this is to calculate the similarity between the intermediate result and also the final result. In this way, I think it is a good way to trace the reasoning path in the multi-hoop reasoning, which I think is important perspective to think about in the current open-ended reasoning tasks. And similar to the previous comparison with answer-only option, this one also uses a way to make sure that it is the effect of reasoning instead of the knowledge embedded into the models. It just changes the context in the prompt. So it may just use a random context or use an incomplete context to get a return from the large language model. And we can see that when the context is randomly changed, the proposed faithful reasoning result, it is the first row, just can get a not very good performance. But after getting the full context, it will just significantly be boosted. So in this way, it is also a method to prove that the model is actually doing the reasoning instead of using the embedded knowledge. So here's a summary of today's section about common sense reasoning. First one, large language model has some common sense knowledge, but purely increasing the model size alone is not an efficient way to bridge the gap between the human's performance and the large language model's performance. And large language models are easy to be affected by the multiple design choices in the experiment. So there are some more perspectives for us to consider. And the third one is faithful reasoning is an important topic for reasoning research, which means for reasoning tasks, it is really important to think it is the effect of the knowledge embedded in the models, or it is really the effect of the reasoning. Yeah. So this is my section. Thank you.
So today I'll be talking about reasoning systems with LLMs. Unfortunately, we are a bit behind time. I really like questions, but maybe I will like at the end of each paper, then I'll open up slots for questions. But you know, if you have any further questions, like we can always take it after class. Okay, so what do I mean by reasoning systems? So let's take a step back and like we're doing all these LLMs because artificial intelligence. We want intelligence, right? And then now we have this revolution called LLMs, and then we can work on things on the LLMs, like prompting, adapters, efficient attention. So these are the works that have been mostly covered so far. But right now, the core of my presentation is why we take a step back and think, okay, now that we have LLMs, can we build a system around the LLM to then reason, like continue to push further the intelligence capabilities? Which brings me to the first paper, Voyager. So essentially what this does is, okay, they use a bunch of LLMs and they use it to play Minecraft. And the interesting thing about it is this thing learns to
try L.
Yeah. So this learning, okay, so when I say previously, like people work on the LLM, so that includes a lot of the very compute intensive stuff, like backprop, adding more layers, tuning and stuff. But okay, throughout this entire my entire presentation, I will cover about how can we enhance LLMs, how can we learn without backprop, okay, like CPU only, no GPUs. All right. So one of the core of this is it learns by writing and using the code that it has written. And what it has achieved is that, like you can see from the graph right here, they can unlock way more items at a very fast pace compared to other just standard LLMs that use prompting methods. Like you can see React Reflection Auto GPT at the lower end of the graph. It can travel a further distance because there is a core element called the curriculum agent that helps it explore to learn. And the most interesting thing is when it learns by like writing and using a code. This code library, I mean, it's just a library. You can actually just take this library and give it to other LLMs to make use and improve their performance. Like, for example, if you see AutoGPT, actually, when they did an experiment where they gave the learn skill library to AutoGPT, it boosts the AutoGPT's performance. So there are three core components of this method. So the first is an automated curriculum, which also challenges one of the paradigms that they're thinking of. You know, when we train LLMs, we shove all the data into it without thinking about what is the order of data for it to learn. But actually, in this work, they have a separate LLM to plan out the curriculum of what to learn. And this is dependent on the exploration progress. So for example, if the core agent like plays a bit of Minecraft and it fails some tasks, this feed is actually fed back to the automatic curriculum to know that, okay, maybe this task is too hard. Let's give you a slightly simpler task. And actually, they found that, of course, in their evaluation studies, this automatic curriculum is important, that it gives us some hints about, like, if you want to make more intelligent agents, maybe we need to think about curriculum learning rather than shoving all the data all at once. So this curriculum then gives a new task to the agent, and there's a whole series of prompting mechanisms for where what it does is, okay, it writes the code, it uses the code to interact with the Minecraft environment. The environment gives it feedback. For example, execution errors, or I have not enough items, for example. So this skill retrieval is retrieving previously written code. And once the task is successful, you can potentially add the code that you've written to the skill library. Or if it fails, then maybe you can refine the program, like update the code to see if it works better. So this is an example of the automatic curriculum. Like you have the current state, you have the agent skill level, propose something to the agent for the agent to do so that it can explore. And the skill library is, okay, so in the top half of this diagram, how does it add new skills? So this assumes that the task is successful. So of course, you generate a program, have a program description. So this is like the standard retrieval augmentation. And at the bottom, actually you can see that both actually the diagrams is quite like retrieval augmentation. But the very important thing about this skill library is it has all these properties which if you only use just LLM, pure LLM, you won't get. So first thing is interpretable, because the code is like this is code, like this is JavaScript code. All right. So humans can read, we know what it's doing as compared to say just the weights. It's composable. So given that you already know one piece of code, of course you can write functions that make use of the functions that you do it, that you have previously written. So you can go up this hierarchy of complexity. It's efficient because if you just call the code, you are not like doing a forward pass. It's transferable, as explained earlier. They actually, when they give the code library to AutoGPT, it can actually enhance the performance. And also it's persistent. It doesn't suffer from like, catastrophic forgetting in neural networks. So some examples of the iterative prompting mechanism, you have environment feedback, like for example, it gets stuck on a task because it needs 2 more sticks. Execution errors, like for example, it needs an item, but it's not there. So of course, so this type of feedback prompts the LM to decide like what to do next. And of course, self-verification, getting an LM to track the state to see if the agent has completed the task. And so this is the rough pseudocode, which actually isn't that long. It's just about, okay, so if you have a curriculum agent, you get an exploration progress based on task you've completed and what you have failed. And then you propose the next task. And okay, let's say for arbitrary like 4 times, let's try to complete the task. All right, so we retrieve the relevant skills, we generate the code based on like the relevant skills and all these parameters, and then we try the code. Let's see if it works. Yeah, and we check if it's successful or not. And we give it maximum 4 tries. If it succeeds, you can add this code. And if not, then you just recognize as a failure. And one very important thing about it is, when I see people report about this paper, it's like, oh, look, it's an LLM for games, an LLM for Minecraft. You are missing the point. As mentioned earlier in the skills library, the skills library solves a lot of the problems that LLMs alone couldn't handle. And at the same time, if you look at this pseudocode, it's not very Minecraft specific. It's just about learning. This is about intelligence. So just so that you don't confuse it with LLM for games. However, of course, there are always limitations for this. Like for example, this is text only. It can definitely benefit a lot from visuals. Occasional failures in self-verification. Actually, like I remember when Prof mentioned very early on in the class, sometimes you have to look into the appendix for a lot of more interesting details. I read the entire code base and the appendix, and turns out there's actually still a lot of handcrafting and domain-specific knowledge. Like for example, you see here, in their prompts, all the placing, building, planting, trading tasks should be avoided. Do not propose tasks starting with this. Like I don't, how am I supposed to know about this, right? So occasional hallucination, because this is very open-ended. You can write code and therefore like you can potentially call functions or inputs that don't exist. Yeah. And yeah, so this is for the Voyager. Okay, I'll take questions.
They mentioned that you need additional visuals and all that, right? Has there been any attempts to combine this with image recognition and so on?
I believe there were previous attempts, but not in the Voyager context. Right. But the thing is, the amazing thing is like from text only, you can really achieve quite a lot. And if you combine with visuals, it's definitely way more powerful.
And what about real world robotics?
Real world robotics. Yeah, I think that there were some papers, but at least in the Voyager context, they didn't use the visuals. But for robotics, I'm quite sure there are some papers out there.
Yeah, I mean, I have a question.
I'm thinking.
So this is and yeah, it's quite interesting. So can you go back to the slide when you talk about episode and so on?
Sorry, when which slide?
Yeah, this one.
Yeah.
So why is efficient? Because I think the cost here is not so efficient.
Oh, okay. This efficient part is something that I wrote, but it's more like, okay, if you want to do things a bunch of steps, you want to control like a Minecraft environment. Like if we totally ignore the skill library, you probably need a couple of forward passes in the neural network. Compared to like you call a piece of code, which okay, I know this is a bit hand wavy, but okay, this efficient part I wrote it. It's not all others.
Yeah.
But in my opinion, I'd rather call a function than to do like multiple forward passes.
I see. Yeah. So I mean, in terms of deployment, it is probably efficient, but in terms of cost, then like calling a lot of
Yeah.
okay.
Yeah, you're right.
Okay. So how about the transfer the code?
Transferable means like, okay, so at least in a lot of the modern agents, right, you have tools, you allow the LLMs to call functions, and you have to provide the functions. So in this skill library, okay, so in Voyager, right, what it talks about is to build your tools, to write functions, build and write even more functions that of a higher complexity that could use your own functions. So whereas most standard work right now is we humans write the functions and give the LLM to do. That's the standard, at least the most common thing right now. But in Voyager, you can get while exploring Minecraft, you end up writing a whole bunch of functions. And these functions are transferable in the sense that you can use these functions and just give to other LLMs. Like in one of their experiments, they gave the library to AutoGPT and it boosts their performance.
I see.
Yeah.
So one last question I have in the last slide that you showed it on. So we were saying that to avoid overplacing, delay planting, it should be avoided. So can the model really avoid and do not propose that starting with? Because
Yeah, I'm not sure because I haven't actually run like the code, even though I read the code but I haven't run. Yeah, but I put this thing in there mainly because just to show the point about handcrafting and heavy prompt engineering. Yeah, that I really like this piece of work, but you still need to it still requires a lot of like all this handcrafting and prompt engineering to get it working. Yeah, so there's still a long way to go. Yeah.
Next, my question is that how specifically how you use language to interact with the Minecraft?
Via API. So when I put here APIs are in context. Okay, so the interaction is via open source library called MindFlayer. So it's a bunch of function calls. So the LLMs they wrote the like, okay, these are some available APIs you have. These are the descriptions of what it does and examples, and then call these functions in order to interact with the environment.
So my follow-up question is that so actually Minecraft is sort of a simulator for the world.
Yes.
Right? Then
yes.
What do you think is the major limitations of the property that it has missed about the actual property of our world instead of a simulated world?
Yeah, I mean, I think there's definitely quite a lot of like gaps, but it's a good start. It's a good start, I guess.
Okay.
Yeah.
Thanks.
Yeah, so I think if you look at any embedded systems work, especially like robotics, you always see that simulations don't hold up to the real environment. There's so much noise in our real environment, like you just try to ask a robot to move 1 meter forward, it moves 0.96 and it's slightly slanted. All of these things, they accumulate and they cause things to fail. So simulation does not equal real world environments, right? So there's a lot of control problems that people have been looking at for decades in the engineering department, that come into play here. The other thing is that I think when you look at real world systems, there's a lot of problems with engineering good reward models, right? Like in Voyager, if you succeed at making an object, it just poof, it appears, right? So then you know that you have a new object, right? But if you try to make something in the real world, you succeed 90% of the 90%. Does it mean that you have the thing that you were trying to make, right? So it's hard. I mean, it's not as binary as our simulation world makes it. So this is a definite simplification.
Yeah, okay. Next, I'll go on to Ghosts in the Minecraft. It's actually
Is there a comment on chat? Can you just press the chat button there?
Oh, okay.
Okay, never mind. So Shang, I guess you answered your own question. Yeah, if you want to ask, yeah, just put in the chat or speak out because we can hear you if you unmute your mic. Yeah, go ahead.
Yeah, so GITM is very related to Voyager in a sense that like it's about accomplishing tasks, unlocking like the objects and stuff. However, this part will be slightly shorter because the code is not available. So I haven't understood it like as well as the others. Their achievement is they unlock the full tech tree, whereas previous ages only 30%. But note that GITM and Voyager came out about the same time. So I don't think GITM has seen Voyager yet. And it has stronger emphasis on task decomposition and planning. And takes only 2 days to train on CPU. And you can see from this graph, like I don't think it's that fair a comparison, but you can see how like when they just think about how to make this system around the LLM and to train and get the success rate is way better than training like directly LLMs. And this is a graph to show like the difference between RL versus GITM, that there's a lot of like things in between: decomposing, planning, selecting actions before interacting with the environment. So this is their rough workflow with these boxes are my own annotation. So initially, when it receives a goal, it decomposes the goal in a standard like rack style and recursive decomposition. The interesting thing is that the decompose function is available in Voyager, but it's not used. So, and they claim that they use rack but in the paper, but not in the code. So okay, maybe there's some differences here. So now that we have the sub goals, there's a planner that uses a bunch of the memory to then select the structure. So the key difference between GITM and Voyager is that for Voyager, it's very open-ended. You can write whatever code you want. Okay, you have the APIs, and then you can write like any code you want. Whereas for GITM, it's a structured action set. There are only 9 functions. You don't actually learn the functions. These functions are condensed from, okay, so apparently there are 3141 available actions that they condense into 9 actions by merging frequent actions and functionalities. But unfortunately, like the paper didn't describe it that well, and there's no code. So I don't really know how this happened. But they constrain the space to 9 functions. And what they do is their core output is the LLM planner, given this action space on 9 functions, sequences the action. So they choose which action, which bunch of actions in which sequence, and the inputs to the functions, and then executes it in the environment. So that's the difference. This is a more constrained action space. Yeah. So in the planning, they make use of the memory. So there's this thing called a reference plan. That means like if your plan succeeds, this sequence of actions gets stored in the memory. So that's their equivalent of a skills library. And then from the query, a bunch of prompts, then you get the model to then plan out, okay, what you should do. And what I find interesting about this is this thing about skills consolidation. So when doing a task, okay, then there's a sequence of actions that accomplish the task. But sometimes there may be some differences. Like apparently in Minecraft, day and night makes a difference. So what they do is after accumulating many ways to accomplish a task, the LLM then consolidates these multiple sequences into one sequence that's supposed to handle all of them. So there's this form of skills consolidation right here. Yeah, okay. Okay, any quick questions?
Questions? Yeah, so like two questions are. Number one would be like you said that Voyager doesn't use RAG in the code, right? But I thought in the skills.py it uses
no. Okay. When I say RAG at the start, I mean from wiki. Yeah, like for example, using text-based knowledge about Minecraft. Yeah.
Oh, yes.
Yeah. Oh yeah, I probably should edit that part. Yeah.
And also for like for Voyager and both the goals in the Minecraft, right? Because usually like for reinforcement learning, like right, there's usually like some sort of like exploration/exploitation ratio.
Yeah.
Is there something similar in Voyager or goals in the Minecraft where they see whether like if the skill, like for a certain skill, right, they have a ratio whether they retrieve it from the skill tree or whether they just generate the skill even though it might be in the skill tree.
Yeah, I think this is like one of the bigger problems. It's not very explicit in both works. Like for example, in Voyager, right, you will always retrieve the skill. You will always retrieve the skill. So it may not be yeah, and it may potentially be a case that it keeps adding a lot of things to the skill library that may cause like some confusion. Yeah. So it's not that explicit. Yeah, but they, at least for exploration, Voyager has the curriculum agent that implicitly maybe there's some form of reasoning about like maybe you should explore more, or like maybe this one is too hard for you and stuff. Yeah.
Thank you.
Okay. Then next is generative agents. Okay, so for this work, right, they make a bunch of characters with personalities and they just interact with each other in this like simulated world. And this like example of a daily life, like the agents wake up, then they pack, they go to work and stuff. And the core result for this is this thing called believability. So after letting the agents run loose, so apparently in their experiments, they set up 25 agents and they let them do whatever they want for 2 days in that world. And at the end of it, they interview the agents and like ask it questions, get some answers. At the same time, they ask a human to look at this system, look at the agents and their personalities and ask the same question, like if you are the agent, what would you have answered? And then they compare like how hard it is to distinguish between like human and just the agent's answer. So this is a bit more like Turing test style. And what they found is like without their core components, okay, the agent's answers are not believable. But the moment you start adding one or more of the components, the agents become more believable to the point that it's hard for humans to distinguish it between it and another human generated response. So how do they achieve it? So again, in two broad strokes. Okay, there are multiple memory components and multiple cognitive components. For the cognitive components, first it perceives. So apparently it has a spatial memory where you only see like in your surroundings, and these whatever you perceive. Okay, so everything gets put in the memory stream. It may if you see something new, you may trigger some like memories for you to potentially act on. And at the end of the day or start of the day, you may do your own planning and reflection. So in memory, agents remember things as a subgraph. So the spatial memory, associative memory would be like okay, in this subject predicate object, like Tom is eating like a sandwich or something. It's also associated with keywords, and mainly because for all in the memory retrieval part, they also retrieve based on a bunch of factors that I'll go on in the next slide. And then the scratch memory, memory involving like a slightly more short-term memory about like your own identity, what you have planned, what's your current status, what are you doing right now. So I think the one crux of this paper is memory stream is just like it's basically logs, like they just spam like the full logs. When they want to retrieve something, like to recall from a memory, they have three metrics. One is recency. When was the last time you retrieved it? Next is importance. It's basically every time you have a thought or an observation, you get an LM to try to rate how important it is to you. And next is relevance. Relevance is just like embedding. So they sort of like combine these scores to form some form of like memory model. Yeah, and this is being used when it's like reflecting or like revising its identity or chatting with others. So it does planning. So at every start of the day, it does like task decomposition. It revises its own identity. It can potentially react to new observations which interrupts its plan. And another important point is the reflection, because in the raw memory log, it's just person is doing this, thing is doing that. And these are raw observations, but to get higher level thoughts, you need some form of reflection. For example, over here, right? One of the observations is this person is reading about urban design. This person is reading about gentrification. This person is discussing his research with a librarian. So these are just like very isolated things. But as you keep reflecting, you finally figure out something more higher level. This person is very dedicated towards research. And the thing is, how does it work? So there's a certain like threshold that you need to cross, and then you start reflecting. So it prompts the LLMs and the recent 100 most recent records to ask, what should I reflect on? And then now you have the questions of what you should reflect on. Then again, you retrieve the relevant memories and ask the LLM to extract insights. Some limitations, there's a bit of hallucination, but it's not that wild. It's mostly embellishment. Inheritance of underlying LLM. So they tend to be quite formal, and they confuse between agents and people in the real world. Like there's an agent called Adam Smith, but there's also an Adam Smith in our real world. And sometimes there was a bit of confusion in the discussions. And strangely, like as the knowledge expands, sometimes the believability like decreases, and there's a lack of like social norms. Yeah. So okay, I'll take some questions if any. Okay, and then I'll move on.
How is going to a nearby bar not believable?
Oh, for lunch. Like after discovering it, they go there very frequently for lunch, as opposed to like cafeteria. At least that's the author's opinion that it's not normal. Yeah.
Maybe a social thing.
Yeah, it's a social thing. Okay, so right now, after discussing, so these are the three core papers that I discussed. Now let's take a step back and look at patterns. Like, after seeing all this, is there a way for us to properly think about like all these intelligent agents or like systems of intelligence that like you can see like from this interacting with the environment, having some things to like having a separate memory component like internal reasoning, and it seems like okay, this is like some like new wave or something, except it's not new. Okay, so people have been thinking about like how all like things like memory like planning, etc. How they all interact a very, very long time ago, but they did not see much success. But we ask ourselves, why is this so? And why am I bringing this whole cognitive architecture up? So before people mistake me for like trying to go crackpot, let me so like recently there was this paper, Cognitive Architectures for Language Agents. You must know that one of the authors is actually also on the orders of React, Reflection, and Tree of Thoughts. So one of the authors has spent a lot of time thinking about like a lot of the prompting stuff, and now they sort of pivot. And let's take a look why is this so? All right. So cognitive architecture is just models of human cognition. You explicitly instantiate all these components and potentially even more. And actually, at that point in time when cognitive architecture came out, eventually there are hundreds of architectures with like thousands of papers around it. So this koala paper is a concept paper. What they do is they learn from the past. They read what about all the insights from cognitive architecture research. Then, of course, they combine their current expertise in what agents are like. When you see generative agents and Voyager, they also learn from it, and they put into like a framework to try to explain all the little components there are, and then propose a modern version. So if you find gaps in the framework, that's actually future work, and that's exactly what they are trying to do. So what's different this time? Like cognitive architectures didn't work that well back in the past, because a lot of the things when you want to do reasoning, already back then, like you only have like logical predicates, pre-specified rules and stuff. But right now, one of the things you can do is just to directly ask the LLM, just reason it for me, even though it's not perfect, but it's a component that enables like new things. So the core diagram right here, ignore the words outside is my own annotation, but this is what the authors try to fit into the paper. Yeah, the thing is I only have limited time, and this paper alone, the koala paper, deserves an entire presentation on its own, but I'll try to like distill it. Okay, so I very strongly encourage all of you to read this, because everything you see here, like, okay, this arrow about prompt, this thing about pass, this thing about retrieval, this thing about learning, retrieval, learning, and all these things acting together is rooted in some work somewhere that tried some of these techniques, and the authors just sort of like concatenated all these things to form this structure to help us understand what's going on and how do we build better ones. So for example, right, okay, so on the top here is long-term memory, and they split into procedural, so things that are in the code or LLM, semantic, which is like the world and self-knowledge, and episodic, which is like your past experiences. So for example, in generative agents, this episodic memory is the memory tree, and this semantic memory is the memories of its reflections. Procedural memory, well, for Voyager, that's the skills library. And then you have this working memory. So that is like your short-term memory that's really available. So in Gen agents, it's the scratch memory. Yeah, so, and all the retrieval and learning components, for example, in Voyager, the reasoning comes in the curriculum management and the coding. And then the learning comes when, the skills help the code helps the agent succeed, then it gets placed in the long-term procedural memory. That's for Voyager. And then when it reflects, that's another form of reasoning that goes into this reflection right here. So they have this section where it's actionable insights. Like it's also quite a long segment, but I just took out some of the things that I find interesting. One is memory beyond retrieval augmentation. For example, is it possible that there are techniques that, okay, not just human knowledge, but self-discovered knowledge, like potentially Voyager, and self-maintained experience, knowledge, and skills. So I don't think there's a framework that covers all of these yet. Maybe some words cover a bit here and there. Learning beyond in-context learning and fine-tuning. Like for example, right, in this diagram, there's learning here, there's learning here, there's learning here. There are many ways to learn. And the papers so far have only implemented a bit of this here and there. Then can we combine all these multiple forms of learning to create better agents, for example? And then beyond action, decision making beyond action generation, solving overconfidence, miscalibration, for example, learn new decision-making procedures, because all the while, it's our human code that sort of extracts the decisions from these LLMs. Yeah, so it seems like this might be the way to go. And my closing comment is that like yeah, you know, it's quite a new thing. I'm actually quite excited about it. You know, if any of you are interested to discuss more, like yeah, please do. Okay, yeah, this is the end of my presentation. Maybe I'll take maybe some short questions, and then like if you have longer questions.
Okay, let's first thank our presenter. Question. I think this is a really nice paper because I think it's like an overarching framework. It's like a Christmas tree where you dangle individual papers as ornaments on the tree, right? So you have an overall architecture and you know where things are going. So yeah, I think there are still parts that are probably missing from the architecture, but it takes some experience or some long-term thinking thought to project what is missing from those diagrams. But like you said, people have been thinking about many of these types of representation issues all the way back since the beginning of computer science. You know, these things people have thought of, but they didn't have the tools to realize a lot of what things were defined. Right now that we have a large language model, which is very easy to interact with and creates feasible outputs, it becomes easier to think about them. But definitely, when you look at the architecture of the diagram that you had, where you put the Voyager as well as the generative agent papers there, and you generalized labels to each part, there's obviously customizations of how those processes can be used that need to be done to a large language model or any other foundation model to better accomplish those tasks. So do you guys have any reflections or like to add anything? Yeah, I'll be very happy to talk with you more about it later.
Actually, for like the agents, right? Like I see that I observe that a lot of those papers, what they do that they split like a lot of those like one agent to multiple agents, right? So my question is more of how and why. Like how do the authors split the agents? Like what's their methodology for splitting like the task into multiple agents? Like how do they actually split tasks up? Like let's say for Voyager's action, critique, and curriculum, right? How did authors come up like, oh, I need an agent for action, I need an agent for critique, I need an agent for curriculum?
Yeah, actually, like it's a good question. A lot of it is still maybe handcrafted, maybe because like I believe we had an earlier discussion about like maybe because of context length, maybe because of like a drift, because if you have one LM and in the system prompt you give it too many rows, it may end up confusing the rows. But okay, actually in the Koala paper, they did discuss, okay, so in the discussion section, they did have mentioned some thoughts on like when to use LM, when to use code. I cannot remember at the top of my head, but it's in the discussion section of the paper, some of their own thoughts. Yeah.
Thank you.
Okay.
Okay, so we have our next presenter.
Yeah, I think it's quite a short one. Okay, so we go back to in context learning actually, where we ask the question, can we what can we do to further is reasoning from LLMs via better prompting before we hit the hard limit of the language model's ability? So here are some approaches that I will discuss today, which actually addresses some of the problems that people have encountered with earlier with chain of thought reasoning. One of them is actually even with chain of thought reasoning, they found that actually the language models are not very good at solving problems which require like putting together, generalizing from like many smaller problems. So one way of doing it is actually to just teach the LMs to decompose the problems and then feed the decomposed problems. And second approach is actually to addresses the problem where actually in chain of thought reasoning, you need to construct the problems, the examples on your own. So the question is, can you make the LMs do it for you? Another one which actually addresses is more for numerical mathematical reasoning is to get the LMs to rewrite either the problems or its intermediate steps as code, or actually generate its final answer as code. So we first go to the first approach, which is decomposition. So the paper that does this is actually known as called it least to most prompting. So they said that they were inspired by educational pedagogy where in order to teach a student, right, you actually break it down into smaller tasks, which might intersect with what the student already knows. So this prompting strategy actually has two parts. One is you have a prompt that gets the LLMs to decompose the question in subproblems. And then based on the subproblems that it has been decomposed, you feed it back to the LLM and get it to get the final answer. So actually the first part, decomposing the questions into sub-questions, can be done in a zero-shot manner. But for better results, the paper actually did it via some like examples. So these are their evaluation results, where they actually evaluated on 3 types of problems: symbolic, compositional, and math reasoning. So for symbolic reasoning, they found that yes, it does better than the LMs especially on longer problems. Okay, symbolic reasoning, this particular example that they use is actually just to identify the last letter. And they found that the LMs do better with these two most prompting as the length goes longer. But the error cases that they found actually kind of highlights the limitations of the LM, as your chain of words gets longer, right? The LM starts like making results errors due to like maybe dropping some words, or basically it can identify the last letter of the words, but it just cannot assemble it properly as your chain length gets longer. So so for composition, no generalization, which is actually the main motivation of this paper, they tested it on this problem where it's basically a sequence problem based on instructions, then give it generate the sequence of actions that satisfy that sequence, that instructions. But for compositional generalization, one problem that the LMs have been very weak at is where if your training set has a shorter sequence than the test set, it tends to do not so well with chain of thought. But if you use least to most prompting, it actually has quite a good result. So for math reasoning, your mileage varies. So for like simpler problems, sometimes chain of thought still does better. But as it gets harder, least to most works better. But of course, to an extent, at some point you'll probably hit the limitation of the LM itself. So the limitations of least to most prompting, right, is in order to get the models to decompose the problems well, because how well it decomposes the problem, of course, affects how well it can solve the problem eventually. You need to you still need to handcraft your decomposition prompts. And of course, this actually still relies on the LM's ability to decompose the problems correctly. So they actually tested on smaller models. The main model they used was the DaVinci 2 or 3. But when they tested on the smaller one, they found that actually chain of thought still does better because the LMs just cannot decompose the problem well. Yeah. And of course, you're still bounded by the LM's ability to solve your decomposed problems. So the next one is analogical prompting, where the authors say that they were inspired by how humans reason by analogy. So in order to solve a new problem, they think about the problems, the similar problems that they encountered, and then how do they generalize the new problem. So actually, but one thing I realized this paper does is it's kind of similar to chain of thought, where you actually get the model to print out its immediate reasoning. But here you are trying to do it in zero shot. So you based on the prompts, right, by giving it like an instruction to actually generate the relevant examples and then solve the problem based on this relevant examples, you kind of try to save yourself the trouble of constructing your examples in the chain of thought prompting. And then one variant which the author tried and seems to work better for one problem, which a coding problem which is hard in general for the LLMs, is actually to add one more instruction, which is to get the model to call relevant knowledge first before it generates the examples. And it does better in this case because when you get it to recall the relevant knowledge, this relevant knowledge actually helps frame the examples that the LM generates later. So it kind of generates like more relevant examples as well. So yeah, these are the results. Yeah, they found that on this particular problem, which is apparently hard for the LMs of today, there is some small improvement if you add in knowledge generation. And oh yeah, one more thing I want to point out is, of course, in this case, like nothing is a silver bullet. And in this case, in some cases, right, in some problems, chain of thought reasoning with maybe some degree of handcrafting prompts still work better. Yeah. So yeah, again, the limitations is you are still riding on the LM's ability to generate relevant and correct exemplars. And of course, if it generates like irrelevant exemplars, right, as like some work has shown, right, actually what you put in irrelevant stuff in the context actually affects can very greatly and negatively affect your model's ability to output the result that you want. So, and because of this, it does not work well on smaller and less powerful models. Yeah. And sometimes even when it generates like relevant exemplars, it still might get misdirected, or maybe it just zooms in, it focuses too much on a particular example and fails to generalize. So for code or program prompting, there are two motivations for it. One is sometimes natural language has a bit of ambiguities, which maybe affects how well your model can interpret the question. Two is LMs can't really count, or LMs cannot really count when your numbers are big, because presumably bigger numbers or less, bigger numbers tend to occur less often also in their training set. So there are a few papers that did it. The earlier one is known as program of thoughts, where, well, essentially the high level idea is you prompt the model to output a program that solves it, and then you just ship out the program to output the answer. So you do not rely on the model's ability to count or anything. So there are two ways. One way is, of course, I'll give you examples of code that solves like similar problems. And then two is zero shot. So they found that, I believe this is actually on the few shot case. They claim that this method still works on the LMs that are not optimized for code. And these are the examples that we give. But I realized that these are most recent models, and these are models that are trained on a lot of web data, which of course includes code, because like you have Stack Overflow. Yeah. So another similar approach, but in this case, is known as program-aided LM. But in this case, what they do is they get the model to output its intermediate steps as code. So it reasons in code rather than natural language. This is actually a few shot prompting method. So in the prompt, you actually give it some examples of how you do that, and then the model is expected to generalize it to the questions that it has. So yeah, again, same trend. It outperforms chain of thought if you have a strong enough LM, and in this case, maybe it's better if your LM, is trained on code. Although, if you have GPT-3, which is not optimized for code, but its training includes code, you'll probably do quite well as well. So this is another method, but in this case, they actually they broke it down into stage. And in stage 2, they actually they tried two things. One is either to based on the code that the model generated in stage 1, either get the model to output the answer to it via somehow iterative prompting, where if it's wrong, I think you give it some tweaks such that the final answer, such that it will guide it towards the final answer, or you actually feed the code into a Python interpreter or something that can detect errors. Then you feed the errors together the code to the model, so such that the model refines its own code. So so there are two ways. One is you you somehow get the model to solve its own code, or you ship the code out, but if the code doesn't work, then you get the model refine the code based on the errors that you encounter. So they tried two methods, so as usual. So for the zero shot case, right, there are two tricks, additional tricks that they tried. So one is they actually told it that some things that in the prompt might be irrelevant. And another thing that they tried that seems to work very well is other symbolic library. Yeah. So these are the results. As you can see, somehow adding an additional prompt that tells it that some of the things that you have given it might be irrelevant improves the results. And of course, teaching it to use a particular code library a particular code library actually can improve the results. So they found that with these tricks, apparently it does better than an earlier method, which is program-aided language. The difference is, of course, in this case, is zero shot, whereas the previous one requires some handcrafting of examples. And yeah, again, same limitations. And they found that actually with the few short examples where you actually teach it to decompose it in the code, right? How you name a variable matters. I guess it kind of makes sense because based on the training text, right? Relevant, I mean, the program might have already encountered relevant programs in its training data. And if you use the correct variable names, you can probably elicit the relevant code from the training data. Yeah. So there are some other ideas that I encountered that tries to address the problem that LLMs can't count. The first method is kind of cute. So basically, they actually identify the numbers in the problem sum. They replace it with smaller numbers while keeping the ordering of the numbers. So then they send out the LLMs, of course, output a solution based on these smaller numbers. Then they send it to a linear solver to try to deduce the relationship that the model has. Things that these numbers have with each other. It's kind of cute, but it's not very generalizable because it only works if you can express it as a linear system. And the other way is to actually replace the numbers with symbols. But they found that in this case, right, if you give it the algebra problem, which is output, it might be wrong. But if you combine the algebra question, which is output to this answer, it's answer to that question, and then you replace the numbers in the original question with symbols. In some cases, you can actually get the number to the LM to output the equation that describes the relationship between the numbers. But okay, it's not very clear how far this method can go. And yeah, maybe you are also limited to simple linear problems. Yeah. So one trick that some of the prompting papers that have used is, of course, ensemble methods. So one is self-consistency, where actually you keep running the same prompt, but with a different temperature. Then you actually group the prompts together. Based on some voting, you select the answer that occurs most frequently. Another way is, of course, you have multiple prompts, then you select the most frequent answer, or you have the luxury of having multiple LLMs, then yeah. So yeah, here's a recent paper which tries to put together all tricks that you have. For one is sampling, so the different ways of generating the answers, ways of actually determining whether based on the answer of the LM, should you regenerate the answer or not, and then ways of selecting the answers of the LMs. So yeah, that's all I have for today. So yeah.
Can you explain this diagram a bit more? What's going on?
So in this framework, which, okay, I actually haven't had time to really dive into the paper itself, but I found it interesting because like given enough time, people would tend to try to come up with a mother of all things kind of framework. So here, right, the framework that they have actually like tries to like automatically decide based on the whatever the LM has given for a prompt, whether or not you should like send it back to the LM for further refinement, so that you can like, yeah, so that you can get better answers. And another thing that it does is it actually collects, like in the case where you actually do an example of prompt scenario, it has a variety of methods that you can select to actually choose the best answer from that multiple prompt result. Yeah. So.
Okay, let's thank our speaker. Do we have any questions for any of our presenters? Okay, so again, just to remind everyone, we need to have you fill in the worksheet. So please do that as soon as you can. And then we have next week, again, your sprint 3 is due. That means you should be finishing up your second sprint for development. Again, we see generally in 6101, people get too ambitious at the beginning, and then they find out they have to scale back their projects quite a bit. So please do check in if you are having difficulty completing your project, okay, because it's fine. We just want you to have more experience with language models, and then be able to work on something together, hopefully with more than one person. Okay, so that's all we have for today. So let's thank all of our speakers again. Okay, and that's all. Thank you so much.
So are we